This question is about enthalpy changes. When ethanoic acid, so here's our ethanoic acid, here's the formula, reacts with sodium hydroxide, the enthalpy change is minus 56.1, so exothermic. Calculate the temperature rise when 25 centimetres cubed, so let's just have a look, of 2 molar ethanoic acid reacts with 25 centimetres cubed of 2 molar sodium hydroxide. So we can see before we even calculate that the moles of each of these is identical, and since they're 1-to-1 in the equation, neither is in excess, they're in the exact right reacting quantities, so we can just work out the moles of either, and it will be the moles that we would need to use. So we're going to do moles are volume times concentration. Moles are very clever, and we're going to calculate that, and we're going to get 0.05 moles. Now, like we said, because it's the same for both and they're 1-to-1 in the equation, these are the reacting quantities, so we only need to calculate the moles of one. We know that the delta H value is minus 56.1 kilojoules per mole, and that we've got 0.05 moles, so we can work out the heat enthalpy, the heat energy change for our 0.05 moles by saying 56.1 kilojoules of energy are released for every mole, but we've only got 0.05. We can lose the minus sign because the minus sign just means energy released. And so because we're saying this is the heat released, we don't need it anymore. This is 2.805 kilojoules. But when we want to use this specific heat capacity, we do need that to be in joules. So it's 2,805 joules equals the mass of the solution times the specific heat capacity times the delta T. So 2,805 joules equals the mass of the solution. Now remember that in here you've put actually 25 and another 25. So in total the mass of the solution is 50. It's 50 centimetres cubed, but it tells us the density is 1 gram per centimetre cubed. And we're going to times that by 4.18, and we're going to times that by delta T. So we can rearrange to say that delta T equals 2,805 divided by 50 times 4.18. And we'll get that the delta T is 13.4 degrees C, or 13.4 Kelvin. And so that was our temperature rise, 13.4 degrees C. A student recorded the temperature of aqueous ethanoic acid in a polystyrene cup for 3 minutes. At the 4th minute, the student added some sodium hydrogen carbonate. The student stirred the mixture and carried on recording the temperature every minute for several minutes. The measurements are shown. A best fit line showing the temperature before mixing has been drawn. Draw an appropriate best fit line on figure 2. Now, we're going to have to make some choices. A best fit line can be a curve or a line, and we would need to ignore results that shouldn't be included. Now, in this example, I will rub this out in a minute because it will interfere. This result here shows that the reaction was still happening, and the mixture was still cooling down. We hadn't quite reached the minimum temperature, so we're going to ignore that point. Then we're going to look at all these other points, and we can see that they're not in a straight line, and they do look like they're in a curve. So our line of best fit is actually going to be a curve, and so you'll need to take your paper and you will need to curve through, but we do need to extrapolate that line to the 4th minute. So we need to think, how would this curve end up if we keep going? And so we're going to come back, and we're using a sweeping curve on our piece of paper. And we're trying to get that curving shape as best we can. That sort of curve of best fit there. So what was the temperature change at the time of mixing? We're going to draw a vertical line between the point at the time of mixing was 4 minutes. So we're going to look at the gap at 4 minutes. So we've got 17.2 minus 11.2. And so we can see that for my curve, and you will get a bit of leeway on this, I'm getting a value of 6 degrees C.